All right, hello everyone. It is Dr. Gallenstein, and I am back again with the next Applied Econometrics 1 lecture. This is lecture number 11, and it is on the topic of truncated data. This lecture is going to look somewhat similar to our last lecture in which we talked about censored data. Here we're going to discuss a related issue where we have entirely missing values in our dependent variable. All right, so this continues our series on limited dependent variable models, and in this case we're looking at a truncated dependent variable. All right, so without further ado, let us begin lecture number 11, truncated data. All right, what's truncated data? As I go through this lecture, I'm going to talk about two examples. One of which I'm just going to call truncated data, or when we have truncation in our dependent variable. And then the second example, I'm going to talk about what I'm going to call incidental truncation. Okay, and there are two different examples of truncation in our data, and they require different responses, different means of handling them when we try to solve the corresponding issues or problems that arise. All right, so first I'm going to talk about just truncation, and then I'm going to talk about incidental truncation later. All right, so then let's move forward with that. Truncated data. We're going to talk about truncation. All right, now you'll see that there are going to be some similarities here between truncation and censored data, like we talked about in the last lecture. If you remember, censored data was where we were missing information from our data set because our data was constrained by some maximum or some minimum value. I believe the example that I gave in last lecture was the example of income, which I'll use again. And we said that, well, what if when the data was being collected, they didn't collect information on people that made more than $100,000 a year, but instead, everyone that made more than $100,000 a year was simply given the value 100,000. And so that in that case, we're missing information from our data set. We know that there are certain people that make $100,000 a year or more, but we don't know how much more. They're somewhere at or above the 100,000 mark. But we don't know the information about them above that threshold, okay? So that was censoring. That was censoring data. All right, truncation is very similar in the sense that, again, we are missing information from our data set. Okay? But in the example of truncation, what happens is that above or below a threshold, the data does not exist. It's not even in our data set. That means okay, so let me use an example here. I'm going to use a slightly different example, but still using income. So imagine that we're studying factors that determine the income of small farmers, okay? And we use a data set that was collected for low income and middle income households. And therefore, we did not collect data for households with income greater, okay, we're working in Ghana again, okay, greater than 18,000 Ghana cedis per year. So in this case, the income variable is truncated at 18,000. In this case, we did not even collect data on those people that are above 18,000. All right, so that means they're missing from our data set entirely. We don't have data on those people that have income above 18,000. We either don't have information about any variables about them, or we don't have information just about their income variable. Okay, but either way, the data is missing from our data set entirely. What do I mean by that? Let me show an example here. So just like before, just like in the last lecture where you censoring, I talked about, okay, everyone has like a true income, like the true income that they have. But we don't observe the true income, we observe the truncated income if we have a truncated dependent variable. And so what that means is that we observe the true income, so long as that income is not above some cutoff threshold. In our example, we said that the cutoff threshold is 18,000, and so what we see here is that if they have 5,000 income, we observe that we have data on the person who has 5,000 annual income, and we have data on the person who has 17,000 annual income, and we have data on the person that has 13,000 in annual income. But this person who has 20,000 in annual income, the data is missing. So I just use this dot to represent missing data. The data is not there. All right, and again, we have that same problem here. This person makes 19,000, and the data is just not there. It's entirely missing from the data set. All right, that's what truncation would look like. All right, is that the data would be missing. Now, it might be that just the dependent variable is missing, but we have information on other variables like independent variables. Or it could be that we don't even have any information on the independent variables. We just simply have no information whatsoever on those individuals. Either way, what we have is that the data is truncated. It's truncated at some threshold. All right. Now, let me make this a little bit more formal, all right? So let's say so let income be our dependent variable in a regression model, okay? And so we're looking at this income variable I. But let's say that our data on income is truncated 18,000. So that means that some households make more than 18,000, but we do not observe the income measurement for these households. All right, so that means there exists some true income I star, and income I star is anywhere between 0 and infinity. But however, we do not observe I star. We don't observe the true income. Instead, we observe the truncated variable I, okay? And I is between 0 and 18,000. And so the variable that we observe, I, is equal to I star if I star is less than or equal to 18,000. But if I star is greater than 18,000, it's missing. All right. So it means our variable is truncated 18,000. We do not observe income above 18,000. It's missing from the data set entirely. All right. Now, why is truncation a problem? All right, so what we want is we want to estimate the coefficient from the true population regression model, which would be the regression model of I star regressed on some set of independent variables. And in this example, I have just one independent variable. It maybe is other independent variables. And so we want to know the true value of beta 1. We want to know the true relationship between income I star, the true income value, and the various independent variables, or in this case, independent variable x. So we want to know the true beta 1. All right. However, we don't have I star, we only have I. And so if we ran an ordinary least squares regression model of I on x, all right, we would have different coefficients and a different error term because we have a different regression model of the different dependent variable. If we ran this regression model instead, we would estimate we would get an estimate of alpha 1. All right, we would get alpha 1 hat, the estimated value, and this would be a biased estimate of the population parameter beta 1. All right, so it creates bias. Now, in a minute, I'm going to explain that a little bit more. I'll explain that a little bit more. I want to talk about how to solve this problem. All right, so that's the issue. The issue is that if we have truncation, we will have a biased estimate of the population parameter beta 1. All right, let's try to make some sense of that. And to do so, let's take a look at scatter plots. Okay, so let's imagine that our independent variable here x. Let's imagine that x is land. All right, and so we want to know what's the relationship between income and land ownership. Okay, and so I've got some data on income and I have some data on land. And then here is a scatter plot, okay? And so it's we've plotted out all the different data points in the data set. All right, and if you can look here, I've got some light orange data points, and I have some dark orange, or perhaps we could say brown data. All right, now all of the data points, so that's the light brown, so the orange and the brown, all the data points are the true values, okay? So that's the population data. What you can see here is basically the brown are lined over top of orange. So the orange data points are the orange ones and all of the brown ones. All right. And so that's the population data. That's all the data. All the data that represents the population of farmers are the orange dots. All right, the orange data points. And we can fit a regression line to those orange data points, and that regression line would be this yellow regression curve, okay? And so this yellow regression line, this yellow linear fitted regression line represents the population relationship between income and land. All right, so the slope of this yellow line, the slope of this yellow regression line is going to give us, the marginal effect of land on income on average. All right, but now, if we have truncated data, that means we are missing all of the values above the truncation point, or it could be below the truncation point if we're truncated on the bottom. In the case of this example, we are missing all of the values for income above 18,000. And so we only observe the brown dots. We do not observe the orange dots that you see. So these orange dots, we don't observe those orange dots. We only observe the brown dots. All right, we only observe the data that you can see here in brown. All right, and so if we fit a regression model, but we don't have the information in orange, we only have the information in brown, that when we fit that regression model, we're going to get a different line. And so what you see here in blue, this is the estimated. This is the estimated regression curve here in blue. And actually, my key here, my legend here is not correct. But anyways, I'll just leave it for now and fix it later. The second linear line here, we should have. The second linear line here should represent the blue line. And so basically the blue line here is a regression curve that is fitted to the truncated data. And as you can see, these regression curves, these regression lines are different lines, all right, and they have very different slopes. Which means that our estimated marginal effect of land on income is going to be biased. It's not going to accurately represent the relationship between land and income in the population. All right, so just to make that clear, the beta from the yellow regression curve is the true slope, the true relationship between income and land, and the beta from the blue curve, the estimated slope, all right, is from the regression, the truncated regression, and we can see that the blue beta is not going to be the same as the yellow beta, so therefore our estimate will be biased. Okay. All right, so that's the issue. All right, so detecting truncation. How do we know we have it? The most important thing is that we need to know. We need to basically think about the way the data was collected. We need to understand the sample that we collected the data from. Was the sample collected from? Was our data collected from some subset of the total population? Not the whole. Is our sample data representative of the whole population, or is our sample data representative of some subset of the population? Because if it's representative of the subset, there might be some cutoff. There might be some threshold. We might say that, well, the data was only collected on people that had incomes below a certain amount, or it was only collected on people that had some characteristic. All right, so if that's the case, then we will have truncation. All right. And so if we know that our sample had some cutoff threshold, then we can know that our sample does not represent the full population. All right. Now, so that's the primary means. It's just knowing how the data was collected. We also we may or may not be able to kind of look for truncation in the data set by looking to see if our dependent variable has a lot of missing values. Okay, this doesn't answer the question entirely, but sometimes we can have truncation where we have information on other people in the population, but we just don't have information on the dependent variable. In that case, we will have missing values, and we can look into our data set to see if we have a lot of missing values. All right, but most importantly, we have to combine that with our knowledge of the sample population, the population that was included in our data set. I'll talk about that a little bit more when we get into the data in today's demo. All right, so then what do? We have truncation. Well, the issue, like I mentioned, is that if we have truncation, then our estimate of the population regression, the population relationship between the independent variables, will be biased. Solving this is going to be beyond the scope of this course. However, there is something we can say. Our ordinary least squares, our OLS coefficient estimates, will be unbiased, okay, assuming all of our other ordinary least squares assumptions hold, like there's no omitted variable bias, etc. Assuming that all those hold, our ordinary least squares, our OLS coefficient estimates, will be unbiased, will be an unbiased estimate for the truncated subsample. So that means, if we come back up here, let's say that instead of trying to identify the relationship between income and land for the whole population, let's say that we only wanted to know the relationship between income and land for the truncated sample. That means for farmers that have less than 18,000 Ghana cedis a year in income. If that's the case, then we can say that our estimates are are unbiased for that truncated subsample. We just can't say that they're unbiased for the full population because we're not representing the full population due to the truncation. All right, and so we just have to be careful that basically, if we have a truncated dependent variable and we run an ordinary least squares regression, we have to be careful that our estimates are biased estimates of the population, but as long as the other ordinary least squares assumptions hold, they will be unbiased estimates of that truncated subsample. That is, they will be unbiased for the subgroup or the subpopulation that is characterized by that truncated sample of data. All right, and so when we interpret OLS coefficients from a truncated model, we can interpret them as marginal effects, just as normal, but we need to add this additional caveat that they're only unbiased estimates for the truncated sample. That is for the population that is represented by the data that we have, and not for the population that is outside of the range of the sample. Okay, we can talk about that a little bit more when we get into stata. All right. Oh, you know what? No, I've got a great example. All right, excellent. So let me do an example to make that more clear. All right, so here we go. We want to model the relationship between land ownership and farmer incomes in Ghana. All right, so however, we only collected data on farmers who had income less than 18,000 Ghana cedis per year. All right, so maybe we collected it, or maybe we're using somebody else's data set. All right, but either way, our sample data is truncated at 18,000. All right, so we can estimate a model of incomes as a function of land ownership using ordinary least squares, OLS, and find coefficient estimates beta hat. All right, so beta hat, our coefficient on land. All right, now if our goal is to get a coefficient estimate that will tell us the relationship between land and income for the full population of Ghanaian farmers, the coefficient that we estimate using ordinary least squares will be biased. It will be a biased estimate of the relationship between land and income for the full population of Ghanaian farmers. All right. However, as long as all the other ordinary least squares assumptions hold, and our sample is representative of farmers with less than 18,000 Ghana cedis per year, our coefficient estimates, the beta hats, are an unbiased estimate of the relationship between land and income for the subpopulation of farmers with income less than 18,000 Ghana cedis per year, assuming all the other OLS assumptions hold, such as there's no omitted variable bias. Okay, so really at this stage, truncation gives us it's a matter of interpretation, and it's a matter of what we can say about our conclusions. We cannot conclude that that our coefficient estimates represent the relationship between land and income for the whole population. We can, as long as the other assumptions hold, assume that our betas give us the relationship between land and income for the sample, for the population that is represented by our sample. So that means farmers less than 18,000 Ghana cedis per year. Okay. All right, so that's the quick one. Let's do incidental truncation. This is a little bit more in-depth, okay? We're going to spend a little bit more time on this one. And I'm also going to show you a neat model for solving it, all right? So let's do it. Incidental truncation. Incidental truncation. All right, so just like regular old truncation, incidental truncation is where we have missing values for our dependent variable. There are values that are just missing from the data set. But when with truncation, they were missing because we only observed data above or below some threshold. With incidental truncation, we are missing variables, and this truncation, we're missing values, okay? And this truncation depends on some other variable. It depends on some other variable. All right, again, let me use some examples to make this more clear. All right, so 2 examples. One, going back to savings. I talked about savings in our censoring data lecture. All right, so imagine we're looking at savings behavior, and we want to study what are the factors that affect people's savings behavior, but to look and study savings behavior, we are looking exclusively at savings accounts. Okay, well that means we're not looking at the amount of money that people have saved under their mattress, so to speak. We're only looking at money that they have saved in their savings account. All right, so we have data for the amount of money that people have saved in their savings account. However, we are not able to observe the savings behavior of individuals who do not have savings accounts. Now, they might have savings in some other way. For example, they might keep money at home under their mattress. But we don't observe that because we only are looking at the amount of money that they have in their savings account. And so what we have here is that the amount of money that an individual has saved is missing. That means we're missing it from the data set if they do not have a savings account. All right, so our savings variable is truncated by who does not have a savings account. That means we only observe it for people that have a savings account. If they do not have a savings account, the value of their savings is missing from the data set. So it's truncated. It's missing. We're missing data. It's truncated. And it's truncated by those who do not have a savings account. We do not observe the amount of money that people have saved if they do not have a savings account. All right, so the truncation is dependent upon some other variable, and this other variable is whether or not the person has a savings account. All right, another example. Imagine we want to study the determinants of wages. All right, so we want to collect data on the amount of money, the wage that people would earn in the marketplace. Okay, the amount of money that they would earn in the marketplace. Okay, but we only have wage data on people that are in the workforce. That means we're not able to observe the amount of money that people would make if they were in the workforce. We're not able to observe the wage information for people who are not in the workforce. All right? We're not able to observe, we're not able to observe the wages that people would have earned if they were in the workforce. That means there are people that are not in the workforce. Maybe they're unemployed or they're willingly not engaged in the workforce. Okay. We're not able to observe the wages that they would earn if they were in the market. Okay, so our data is truncated. We do not observe the wage information for people that are not in the workforce. All right, so those are two examples of incidental truncation. In the savings example, the incidental truncation, basically we're missing values. We're missing values for people who do not have savings accounts. All right, so it's truncated by the savings account variable. It's truncated by whether or not someone has a savings account. And in the second example, we study the determinants of wages, and we only observe wages for people who are in the workforce. So it's truncated by whether or not someone is in the workforce. Okay, let me make this a little bit more clear. All right, so incidental truncation. So we have some savings variable, all right, the amount of money that people have saved, okay, but we're using data that comes from people's savings accounts. All right, that means we only observe the amount of money that they have saved if they have a savings account. All right, so that means this variable, the savings variable, is truncated based on another variable. And this other variable is a savings account variable. It equals 1 if they have a savings account. It equals 0 if they do not have a savings account. All right, so that means that if savings account equals 1, that means they have a savings account and we can observe savings. So savings account equals 1, they have savings. This person has 10,000. This person has a savings account, they have this much savings. This person does not have a savings account, which means the data for savings is missing. It's truncated. It's empty. We're missing data. All right. This person does have a savings account, and then we observe the amount of savings they had. This person does not have a savings account. It's empty. We're missing the data. We do not observe their savings. All right. All right, so we do not observe savings for people that do not have a savings account. All right. Making this a little bit more formal, let's say savings. So let savings be a dependent variable in a regression model. So savings star. This is the true savings. Okay, but we only observe S star for those who have a savings account. All right, so let A be this other variable, the savings account variable. All right, so let A be the variable that determines whether or not we observe the data. Okay, so A equals 1 if they have a savings account, and A equals 0 if they do not have a savings account. All right, so we only observe S star when A equals 1. We call A the selection variable. A is the selection variable. A determines whether or not we observe the data or not. A, in this case, is whether or not they have a savings account, and A determines whether or not they have, whether or not we observe the savings data. All right. So therefore, we do not observe the true savings. We do not observe S star. Instead, we observe the truncated variable S. Okay, and the truncated variable S is this: S equals S star if A equals 1. And S equals dot, that means it's missing, it's empty. We don't observe it when A equals 0. All right, so we observe it only when they have a savings account. We do not observe it when they do not have a savings account. All right, so it's truncated by variable A. All right, so why is incidental truncation a problem? All right, so if the dependent variable has incidental truncation, the OLS estimates will most likely be biased. Most likely be biased. It means there's a really good chance that they're going to be biased. It's possible that they won't be, but there's a good chance that they'll be biased. All right, so when will the OLS estimates be biased and when will they be unbiased? All right, when will the OLS estimates, the OLS results, be unbiased? All right, if the source of truncation is random, that means if people who have savings accounts are identical on average to those that don't have savings accounts. If people that have savings accounts are just totally random in the population, some people have them, some people don't. It's totally random who has it, who has the savings account, who doesn't. All right. If it's totally random, that is, if A is uncorrelated with the independent variables, then the OLS estimates will be unbiased. All right. The OLS estimates will be unbiased. All right. So if your selection variable is random, no problem. They're unbiased. You can just use the ordinary least squares regression using your truncated data. Also, if the source of truncation is completely determined by the independent variables, that means if A is purely a function of the independent variables in your model, X, again, no bias, no problem. All right. These two things are unlikely. It's unlikely that these will be the case. All right. It's more likely that we'll have bias. So when will the ordinary least squares results be biased? The ordinary least squares, the OLS results, will be biased if the source of truncation is correlated with the independent variables and not completely determined by them. So basically, if the source of selection, in this case, who has and who does not have a savings account, is not random, which is most likely. It's most likely that there's some reason why some people have savings accounts and some people don't. And so there will be some sort of selection bias. There'll be some sort of bias that's created by this selection variable. Basically, there'll be some sort of bias because there's a certain subset of our sample population that we observe due to this selection variable. All right, I'm going to make that more concrete in a minute. But to summarize this, if we have incidental truncation, we're most likely to have biased results. Usually they'll be biased. The only time they're not biased is if we can say that our selection variable is randomly assigned. That means the people that have savings accounts are just random. Or the people who are in the workforce is just random, okay, which is oftentimes unlikely. All right, or if the source of truncation is completely determined by the independent variables. Okay, if those conditions aren't true, then our OLS estimates will be biased. All right, detecting incidental truncation. How do we know if we have incidental truncation? Again, this is going to be based on our intuition, primarily. We have to think about our dependent variable and think about whether or not there's some sort of incidental truncation. We have to think, if you're studying savings, you have to think, well, with savings, if I'm measuring savings as the amount of money that people have in their savings accounts, then I might have truncation because there might be people that don't have savings accounts. Or if I'm studying wages, I want to know what are the factors that affect the amount of money people earn when they're in the workforce. I might think, well, there are going to be people that are not in the workforce, and therefore I'm not able to observe the amount of money they would make if they were in the labor force. And so you have to think about it intuitively. Think about your dependent variable and think about whether or not there could be a source of incidental truncation. All right, and then you might be able to see some evidence of it in your data set. You can look at your dependent variable in your data set and see if you have a bunch of missing values. And if you do, you can look to see whether or not those missing values depend on some other variable in the data set. Okay, and usually you can do that intuitively. Based on your intuition, you can think about the dependent variable and think about what the source of the incidental truncation might be. I'll give you an example when we do our demo at the end of the lecture. All right, so now, how do we solve the incidental truncation problem? Now, when we did regular truncation, it basically came down to a matter of interpreting the results. In this case, with incidental truncation, we're going to go through and we're going to talk about a nifty, kind of a neat model that we can use to try to address the issue of incidental truncation. All right, and this is going to be called the Heckman sample selection model. The Heckman sample selection model. Sometimes people will call it the Heckett model. I oftentimes just use the full name Heckman sample selection model or just Heckman. Some people will say Heckett model. Okay, and this is a model that we can use to produce unbiased estimates when our dependent variable has incidental truncation. Okay, now I'm going to go into this and explain this. I'm going to go into some detail. I'm not going to go into the full detail. You can learn more about this if you look at Chapter 17 of the Wooldridge text that is assigned for the course. Okay, so I direct you to Chapter 17 of the Wooldridge text to go into this more in detail and to read up on this. But I'm going to try to give you the intuitive understanding of the Heckman model. All right. So to illustrate the Heckman model, I'm going to use our example of savings. Okay. So going back to our example of savings, basically we said that we have a savings variable and it has incidental truncation. We only observe the savings variable for individuals that have a savings account. All right. So let's look at our model. All right. So here we have the OLS model to analyze savings. So we have an OLS model to analyze savings. Here's our savings variable. It's truncated. All right. And here's our our independent variables. I'm using a different notation here. So let me use this notation. If I'm going to put it in bold, what I'm going to say is that beta x in bold represents basically all the coefficients and independent variables. And there can be many different independent variables here. So x1, x2, and so on to xk. So we're saying there's k independent variables here, and then there's an intercept. So I'm just going to use this notation, this bold notation, to represent multiple independent variables. Okay. So here's our OLS regression model where our savings variable is truncated. All right, so S is missing when A equals 0. All right. Now, here's the trick. Here's the thought. This A variable, whether or not you have a savings account, this A variable can be modeled. It means this A variable is a decision. People are choosing whether or not to have a savings account. That means we could model the decision to have a savings account. We can model the decision to have a savings account using a regression model of independent variables. We can conceive of a function that determines the selection decision, that determines whether or not people choose to have a savings account or not, or whether or not people so happen to have a savings account or not. All right. So we can define a model. We can define a model for the A variable. All right. So A is a variable in the data set, and we can model the determinants of A as a function of independent variables. So we can model it as a function of independent variables as well. All right, so we can say this. So let A equal this function. All right, this is kind of an interesting function. Here's the notation. If I have 1 and then brackets, that's a function where the function equals 1 if the inside condition holds, and it's 0 if the inside condition doesn't hold, okay? So A equals 1 if this inside condition holds, and it's 0 if the inside condition doesn't hold. All right, well, this inside condition is basically we have a linear function of independent variables. All right, so I'm using this bold notation again, in this case gamma z, where I'm saying z's are now the independent variables, all right, up to zm, and gammas are my coefficients. All right, so this is basically a different linear model for the decision to have or to not have a savings account. All right, the intuition is that we can model the selection variable. We only observe data for people that have a savings account. All right, so that means when A equals 1. We can model that. We can model that in addition to savings. We're going to model both. We're going to have a model for savings, and we're going to have a model for the decision to have a savings account. All right, we have a model for both of them. Okay. Now, we only observe S when A equals 1. All right? That means that S must somehow depend upon the variables that determine the selection decision in addition to the variables that determine savings. Just think about that intuitively. We only observe savings for people that have a savings account. So just thinking about that intuitively, that means that this savings account variable, or the savings variable, is going to somehow be a function of the variables that determine savings and the variables that determine whether or not you have a savings account, right? Because we only observe people that do have a savings account. So just using that intuition, we need to somehow capture the selection model. We need to somehow capture the effect of the variables that determine the selection process in our analysis of the savings. All right, that's the intuition here. We need to model the selection decision. We need to model A. And we need to somehow include that in our analysis of savings. All right, so with that, and like I said, in chapter 17, the book goes through in some detail how kind of some derivations here. I'm just going to kind of give the intuition in the lecture. Basically, what we're saying is that given this, the expected value, the average savings value, conditional on the variable z and conditional on having a savings account, is going to be a function of the independent variables, the beta x's, but it's also going to be a function of this term, lambda of gamma z. So it's also a function of gamma z, the variables that determine the selection decision. All right, and this lambda variable, all right, rho here is a coefficient. All right, this lambda variable, this is called the this lambda of gamma z is called the inverse Mills ratio. To learn more about it, check out chapter 17. But basically, the inverse Mills ratio is a way of capturing the information in the selection model. Okay. And then rho here, it looks like a P, that's a Greek letter rho. Rho is the coefficient on the inverse Mills ratio. All right. So basically what the Heckman model says is it basically says, we're building up to the Heckman model. All right. So basically what this expression says is that if we were to use the ordinary least squares model that just has savings regressed on beta x, this OLS model, may produce biased estimates. Why? Why would it produce biased estimates? Because if we ran just the ordinary least squares regression model with only beta x, then we would be missing a variable. We would be missing information. The true model is S regressed on beta x plus the inverse Mills ratio, this lambda of gamma z. This inverse Mills ratio is capturing the information from the selection model. All right? And so if we use the ordinary least squares regression, if we use this regression, if we use a regression that does not capture the information from the selection decision, we would have an omitted variable. All right, that means if we use the ordinary least squares regression, if we use this one, if we just regress savings on the independent variables x, we would be creating omitted variable. We would be creating omitted variable bias in our coefficient estimates, if this inverse Mills ratio, if lambda, gamma, z is omitted, and if rho does not equal 0. All right, so that means if the selection decision is basically if it's not random. All right, so that's the intuition. The intuition is that if I use the ordinary least squares regression model, and I do not include the inverse Mills ratio, which captures the effect of the selection process, if I don't do that, then I will be creating omitted variable bias. All right, so the Heckman model allows me to solve that. Okay, let me reinforce a couple things. So there will be omitted variable bias in our OLS regression if we omit the inverse Mills ratio and rho is equal to 0. All right, so if selection is random, that means if who ends up with the savings account is totally random, it's just totally random who has a savings account and who doesn't, which is unlikely. If the selection is random, then rho will equal 0. And there will be no omitted variable bias, and it doesn't matter. We can just use the ordinary least squares regression. We don't have to include the inverse Mills ratio. But if rho does not equal 0, then we will have omitted variable bias if we exclude the inverse Mills ratio. All right? So to solve for incidental truncation and to check for it, or to check for the bias, so to solve incidental truncation, we need to generate the inverse Mills ratio and include it in the OLS regression model. All right, we need to generate it. And how do we generate it? So more explicitly, we can model the selection variable using a probit model. All right, so remember, A is a binary variable. A equals 1 if you have a savings account, and A equals 0 if you don't. And so A is a binary variable. And so we can use a probit model to model A. And if we do that, we can use the estimates from the probit model to calculate the inverse Mills ratio. You can look into the book to go more into detail on that. We'll also do that in the demo. All right, so then what is the Heckman model? The Heckman model is our truncated dependent variable, savings, regressed on the independent variables x plus the estimated inverse Mills ratio from the probit model, where we use a probit model to model the selection variable. All right, so where the inverse Mills ratio comes from a probit model of the selection variable. All right, so then this is our Heckman model. Okay. All right, now there's one very important additional thing to consider when we use the Heckman model. Very, very important. You need to think about this. All right. The Heckman model requires that z, all right, so z is all the independent variables in the selection model. All right, remember from our probit. Okay, z is all the independent variables in our selection model. Our model of A, our model of the selection variable. All right, the Heckman model requires that z, the independent variables in the selection model, all right, include all the independent variables from the savings model. All right, so that is, it includes all the variables from x. All right, so z needs to include all the variables from x plus at least one additional variable. And we call this at least one additional variable, we call it an exclusion restriction. All right, we call it an exclusion restriction. So that means z has to include all of x, has to include all the independent variables in x. I'll illustrate this in data later, make this more clear. Z has to include all the variables from x plus at least one additional variable called an exclusion restriction. All right, what is an exclusion restriction? All right, so an exclusion restriction, we're just going to call it W, all right, some other variable W, all right, is a variable that is correlated with the selection decision, so it's correlated with A, but is not correlated with S. All right, so this exclusion restriction is a variable that is a determinant of the selection decision. That means it's a variable that affects whether or not someone has a savings account. All right, but it does not affect or is not related to how much money they have in their savings. It's not related to how much money they save. It's related only to the source of the selection. All right, this is very, very tricky. It's oftentimes very hard to find a good exclusion restriction. And if you don't have one, then this model won't work. The Heckman model only works if you have a valid exclusion restriction, which means you need to find a variable that is correlated with the selection variable, A in this case, but is not correlated with S, the dependent variable. All right, I'll talk about that more when we do the demo. All right, that can be very tricky at times. And if you do not have that, if you do not have an exclusion restriction, then the Heckman model will not hold. Okay, so just to make that clear, W should not be correlated with S. All right, that means the correlation between them should be 0, statistically 0. All right, and the correlation between A and W should not equal 0. So that means there should be a correlation between the exclusion restriction and the selection variable. Okay. All right, so last thing on that, so when we run the Heckman model, I'll show you in Stata. When we run the Heckman model will generate coefficient estimates for the betas and for rho. Remember, rho is the coefficient on the inverse Mills ratio. All right. If rho is significant, so if your estimate of rho, so if rho hat is insignificant, if it is insignificant, if it's not significant, then we can conclude that there is no selection bias. There's no bias due to the sample selection. That basically the incidental truncation does not cause bias. And in that case, we can simply go back to using the OLS model without the inverse Mills ratio. All right. If rho hat is significant, then we can conclude that there is bias due to the incidental truncation, and that we need to report the betas from the Heckman model rather than the OLS model. All right, so basically the Heckman model is a way for us to both solve the incidental truncation problem and to diagnose whether or not we have an incidental truncation problem. All right, so with the Heckman model, we create the inverse Mills ratio, and then we include it in our regression. And if the inverse Mills ratio is significant, so basically if rho hat is significant, then that tells us that the incidental truncation did cause bias, which means that we need the estimates from the Heckman model. But if rho hat is insignificant, that would mean that the sample selection or the incidental truncation did not create bias, in which case we would simply revert back to the ordinary least squares model. All right. Now, and then lastly, the beta estimates, the beta 1 hat estimates from the Heckman model can be interpreted in the same way as the standard OLS coefficients. So that is that they can be interpreted as marginal effects. All right, so with that, let us do some stata. All right, and so here I've got stata. Oh, I even have results already up, but let's not worry about that yet. All right, so here I have a data set, all right, and this data set is called Ghana Income Data Truncated, all right, so you'll be able to find that online, and you can use this to follow along with the demo, Ghana Income Data Truncated, all right, and I've got two variables in this data set that have truncation, and so we can go through both kinds, all right, so we're going to go through both kinds in this demo. All right, we're going to go through both kinds in this demo. All right, I'm just going to get rid of this because this is the results that I'm going to show you in a minute. So let's just kind of produce some descriptive statistics for the variables in our data set. Just kind of get this off the screen. All right, so let's do it. Lecture 11. Not 111, 11. Lecture 11, truncated data. All right. First, let's just take a look at the data set and take a look at what we have here. I'm going to use two different examples All right, it's going to allow me to illustrate the two different sources of truncation. All right, I'm going to do two different analyses in this demo. The first analysis, I'm going to look at just kind of regular truncation. All right, that's where we have data that's missing above a threshold. All right, and in doing that, I'm going to look at income, and I'm going to say analysis of income. All right, so that's the first example I'm going to do, and in this case, we have an income variable that is truncated. All right, and we know from the way that the data was collected that it is truncated at I think it's 17,000 Ghana cedis in this data set. All right. All right, so let's take a look at the data set. Let's take a look at the data. Now, when we have truncation, basically it can look two ways. One way is where we just don't have any information at all on the people that have more than the threshold. So in that case, our data set would just simply be entirely constrained to people that have less than 17,000 Ghana cedis. Or it might be that we're missing just the dependent variable for people that have more than 17,000 Ghana cedis. In that case, we can see this, and that's actually what I have here. So in this case, all right, so it's called income 2. All right. So in the case of this data set, basically we observe other independent variables for our dependent we see other independent variables for the whole population, but we're missing the income values for people that have more than 17,000. All right. So one way to see this is I can do tab, and our independent variable here is income. Okay, so tab income 2. All right, and comma miss. So that means I'll create a tabulation of the frequency of different income values for the income variable 2, but it will also show me how many variables are missing. So let's click that. Okay, so we've got one person with, all right, so this is Ghana cedis. This is measured in 100 Ghana cedis. So this is 3,700. So one person with 3,700 and etc. All right. So we keep going, and we find, okay, we have 71 observations. So 23% of the sample has missing values. All right, so we have 23% of the sample have missing values, and it looks like it kind of confirms what I was saying, and that is that our data is truncated at 17,000 because we only have observations that are smaller than 17,000. All right, so and we can also look in the data set. So if we look in the data, we can go to income 2, and we can see that we have a lot of missing values. All right, we have a lot of missing values. So it looks like our income 2 variable is truncated. Now, even if I didn't know anything about the way the survey was collected, if I do this, if I do tab income comma miss, I might be suspicious of truncation because I can see that we're missing a lot of values in the dependent variable. But just because we're missing values does not necessarily mean I have truncation. It might be that there was some sort of data collection problem and some people just didn't report their incomes. So I have to know something about where the data came from. But this kind of supports it. This says, all right, I'm missing a bunch of values from my dependent variable. All right. Now, because this is an instructional video and an instructional data set, I happen to have the true income variable in here as well, and that's the variable income. All right, so basically, income 2 is just the income variable, but where all of the values for income above 17,000 are just missing. All right. All right, so then what I can do here, just by means of illustration, is I can just kind of show you what happens when we have truncation. All right, so as a baseline, now normally you would not be able to do this because normally you're not going to have the true income variable. You're not going to have the true dependent variable. If you did, you wouldn't use the truncated one. But just for the sake of illustration, in this data set, I do have the true one, just so I can illustrate the difference. All right, so as a baseline, let's regress income on land and education for the true population income variable. Okay, so like I said, we would not have this normally, but I'm just going to do this to illustrate. All right, so very basic, reg income land edu. All right. Oops. All right, let's shrink this, run it again. All right, here we go. So here is our population estimates. All right. So basically we're saying that this income variable represents the full population of small farmers in northern Ghana. Okay. And so then these are our estimates of the relationship between land and the relationship between land and income and education and income. All right, these are estimates of our true population coefficients. But in real life, if we have truncation, then we do not observe income. Instead, we observe the truncated income variable, which in this data set we're just calling income 2. So now let's do reg income 2 land edu. All right. So here we go. So here is the truncated variable. Here's the income the untruncated variable. You can see that there are 71 fewer observations for the truncated variable than for the true variable. All right. So then let's compare. So the land variable for the full population is 7.9. The land variable, so the coefficient on land for the truncated sample is 3.5. All right, so this is much smaller. It's less than half. Okay, let's compare education. Education for the full sample is 7.34. For the truncated sample, it's 7.71. All right, so this is just a little bit bigger. It's not obvious if this difference would be statistically significant or not. Okay, so what do we have here? Let's recap from the lecture. So what I said was that the coefficients from the truncated OLS model will be biased estimates of the true population relationship. I should maybe clarify for the full population between the dependent variable and the independent variables. All right, so what do we find here? We find that it's quite clearly obvious that the coefficient on land is very different in the truncated sample compared to the untruncated sample. All right, so we see this clearly in looking at the coefficient on land and comparing between the full population for the income variable and the truncated sample from the truncated sample from the income 2 variable. All right. So this confirms this idea that if we have a truncated sample, we will get a biased estimate. We will get biased estimates. So in this case, land is very biased. We can see that land that the coefficient on land from the truncated sample is a biased estimate. It's less than half. All right, so it's biased downwards. Biased downwards. All right. So from the truncated sample is a biased estimate of the full population. All right. All right, so it's very clearly obvious. 3.5 is less than half of 7.9, and so the truncated model, so this is what you would actually see if you had a truncated sample, is that you're going to get a biased estimate. Okay, but like I said in the in the lecture, but the truncated sample can give me an unbiased estimate of the relationship between the dependent and independent variables for the truncated subsample. For the truncated subsample. All right, so that means, all right, so this means that, so basically 3.5, the coefficient on land, so 3.5 is a biased estimate of the relationship between land and income for the population of small farmers in Ghana. But it is, assuming it is an unbiased estimate of the relationship between land and income for small farmers with income below 17,000. So basically, for the subpopulation, all right, assuming, of course, all right, assuming that the other OLS assumptions, so basically no omitted variable bias, and so assume that the other assumptions hold, and the truncated sample is representative of the population of farmers with income below 17,000. Okay. So basically it's a matter of interpretation. This 3.5 is a biased estimate of the relationship between land and income for the full population. However, as long as the other assumptions hold, and as long as this truncated sample is representative of that subset of the population, so farmers below 17,000 Ghana cedis a year, as long as that holds, then this will be an unbiased estimate for that subpopulation. All right. All right, so that is our first analysis. So that's analysis of income, basically example of truncation. Now we're going to do our second example, analysis of fertilizer use. Okay, this is going to be example of incidental truncation. All right, example of incidental truncation. Okay, so now second example, incidental truncation. All right, so let's say that we want to analyze the factors that determine how much fertilizer farmers use on their farms. Okay, so that's what we want to do. We want to study that. But now, as we sit back and we think about it, we recognize that small farmers, if they use fertilizer, we recognize that in this example at least, we recognize that small farmers only have access to fertilizer if they can get a loan to buy it. It is too expensive to buy on their own. All right. So we may have incidental truncation for our fertilizer variable. We might have incidental truncation for our fertilizer variable. The selection variable will be if they received a micro finance loan or not. Okay, so if they have a loan, then they will have fertilizer. If they do not have a loan, they will not have any fertilizer. Okay. All right. So selection is determined by the selection variable microfinance or microloan. All right, so do we have this variable in the data set? Yes, we have microloan. All right, so we have we basically have two situations here. We have our ordinary least squares regression model where we want to look at the determinants of fertilizer use. So in that case, that would be reg, fert, and let's just say it's going to be a function of edu and income. All right, so we just want to look at, what's the effect of education and income on fertilizer use. All right, so this is kind of our, we can say our naive model. All right, this does not consider the truncation. Actually, real quick first, let's just check to make sure this truncation is there. So let's check for truncation. All right, we expect it to be there. We're just going to check for it. Tab, fert, comma, miss. All right, and so if we have a bunch of missing variables, then we can think, all right, we probably have truncation. Yes, we do. 37% of the sample is missing. 133 people are missing from the data set. All right, missing variables. All right, and we think that might be a function of microloan. All right, so there's different ways we can do this. There's different ways we can kind of check for that. Here's one way. Why don't we generate a variable? And let's just call it trunk. All right, so for truncation, and trunk will equal. It'll be a dummy variable. For fert equals this period, which means missing. All right, so trunk will equal 1 if the fertilizer variable is missing, and trunk will equal 0 if it's not. All right, so we're going to create that binary variable. And now I think that the truncation is being determined by microloan. So I'm going to look at the correlation between trunk and microloan. And if I'm correct, then there should be perfect correlation. Microloan. All right, what do we get? It's -1. All right, perfect correlation. So that means that when the truncation variable equals 1, the microloan variable equals 0. All right, so that confirms my theory. The truncation is being determined by the variable microloan. That basically they use fertilizer when they have a microloan. They do not use fertilizer at all. They don't have access to fertilizer if they do not have a loan. All right, so this confirms incidental truncation by the variable microloan. All right, so then we have incidental truncation. Now the naive model, the model that doesn't consider truncation, is just the OLS model regressing fertilizer on education and income. All right, so we can run this model. This is our naive model. All right. Oh, I gotta shrink this down. Okay. But our issue is that if we have this incidental truncation, there's a really good chance that these coefficients are going to be biased. All right. if we have incidental truncation, there is a good chance of bias in these coefficient estimates. All right, so there's a good chance of having bias in the coefficient estimates. All right. All right, so then what we need to do is we need to check to see if we have bias, and we need to solve it. All right, we do both with the Heckman model. We use the Heckman model to both check for bias and solve the bias. All right. Now, in this demo, I'm going to illustrate the Heckman model two ways. I'm going to do it by hand. I'm going to illustrate the Heckman model by hand. That means I'm going to calculate the inverse Mills ratio myself, and use the Stata software program for the Heckman model. All right, we're gonna do both. All right, so let's do both. First, by hand. All right. So what do? We have to estimate the selection model. Step 1, estimate probit model of the selection decision. All right. That would be probit of microloan, regressed on, okay, now remember, step 1, estimate the probit model of the selection decision. All right, remember, the selection model is a function of the independent variables from the lecture of the independent variables z. All right, z includes all the independent variables from the what we might say the main equation, or from the regression of fertilizer on so from the regression of fertilizer. Okay, so z must include education and income. All right, because those are the independent variables from our main regression. All right, so it has to include EDU and income. All right, and it must include an exclusion restriction. All right, this is tricky. We need a valid exclusion restriction. All right, we need a valid exclusion restriction. This is hard. We need a variable that is correlated with or related to the selection variable. All right. That means a variable that determines whether or not someone has a micro loan, all right, but is not correlated with or related to the dependent variable, or we can say maybe the outcome variable of interest. All right, so that means a variable that does not determine fertilizer use. All right, man, that is tricky. That's really, really tricky. All right, and let's go through. We just need to talk through this for a while, because this is going to be the hardest thing. That when you have incidental truncation, the hardest thing The hardest problem that you will confront is identifying a valid exclusion restriction. Okay, so we just need to sit back and talk this through. All right, and what we need to do is we need to go through our data set and we need to see if we have something that we can consider a valid exclusion restriction. Now, the first step, all right, the first step in identifying a valid exclusion restriction is intuition. We have to think about it. All right, we have to think about what makes sense. So let's do it. Let's go through the variables. Education. Will education be correlated, based on your intuition, will education level be correlated with whether or not you have a microloan? I would say yes. I would guess very much so. That basically farmers that are more educated are more likely to look for and avail themselves of microloans. All right. Will education be correlated with how much fertilizer you use? Almost certainly, yes. More well-educated farmers will have access to better information about the advantages of using fertilizer. All right, so education's not going to work. It's not going to work because education is going to be correlated with the use of fertilizer. So that doesn't work. What about land? Well, land is almost certain. I mean, land is definitely going to be related to how much fertilizer you use, because the more land you have, the more fertilizer you're likely to use. So land doesn't work for sure because land will be correlated with fertilizer use. What about gender? Okay, this maybe gender. We can think about this one. Why can we think about this one? Well, it's not obvious to me that men or women would use more fertilizer than that men would use more fertilizer than women, or that women would use more fertilizer than men. However, a lot of microfinance banks give preferential treatment to lending money to women. Okay, so female, that might be a good option. All right, so maybe female, maybe gender, that could be a good option. Let's just kind of do a check. All right, let's look at the correlation between fem and microloan. Yep, that's right. And then the correlation between fem and fertilizer use. Let's just kind of check it, because that might be a good one. That one might work. All right, so let's do correlation fem and microloan. All right. Okay, actually, there's very little correlation between gender and microloan. All right, so then this is not going to be a good one. Gender won't work. There's too little correlation between fem and microloan. Remember, you need to have good correlation between the exclusion restriction and the selection variable, and 0.04 is very low. All right, so that's not going to work. We can check this too. Actually, there's more correlation between gender and fertilizer use in this data set than there is between gender and the microloan. All right, so this will not work. This does not work. All right, so let's keep going. Let's keep thinking. What else might work? Age. Age very well is almost certainly going to be related to how much fertilizer you use, because oftentimes younger farmers are going to be more ready to adopt new technology and more willing to apply more fertilizer. So age is not going to work. Household size. That one's not obvious either way. It's not obvious that household size would be related to whether or not you have a microloan, and it's not obvious that it'd be related to fertilizer use. So that's not a good one. All right, distance. Distance, all right, distance. How far away you are from the market. Okay, let's think about that one. If you live really far away from the market, you're probably much less likely to get a microloan because you have to travel farther to the bank. Okay, so distance should be related to whether or not you have a microloan. Now, will distance to the market be related to how much fertilizer you use? Let's think about that. This is not easy, thinking about this one. Now, you could say that no matter how close you live to the market, once you have fertilizer, it's not going to affect how much fertilizer you will use. In that case, distance might work. Now, you also might argue that if you live farther away from the market, that you will be less likely to know the benefits of fertilizer and you might use less. Okay, but all right, let's just look at it. Maybe distance. All right, now you can tell from this process that picking an exclusion restriction can be difficult, and so I hope that you're seeing that from this demonstration here. I know it's kind of long, but let's check this one. All right, is there a correlation between distance and microloan? Okay, that's a fair amount of correlation, 0.3. All right, negative 0.3. So that means that the farther away you are from the market, the less likely you are to have a microloan. That makes sense, and that's a pretty good amount of correlation. All right, so that checks out. What about correlation between distance and fertilizer use? Okay, there is some correlation here. We have 0.14. That's not a ton, but that's not a lot. It's a little bit. It's a little bit of correlation. That might work. Maybe distance could be used. All right, so maybe let's add distance to our regression model. All right, and let's keep going. Let's keep thinking. We can have more than one exclusion restriction. All right, so let's think fertilizer. That's our variable. Microloan. Well, that's our selection variable, so that doesn't work. Income is one of our independent variables, so that doesn't work. Okay, what's this variable here? Bank friend. Bank friend equals 1 if the farmer knows someone at the bank. All right, let's think about that variable. That's a new one. This variable is, it equals 1 if they have a friend at the bank. Now, why might that affect it? If they know somebody at the bank, they're going to be more likely to get approved for a bank loan. All right, but if they know someone at the bank, that probably has nothing to do with how much fertilizer they use. So that might be a good candidate for an exclusion restriction. All right, so let's check it. Bank friend, microloan. All right, correlation between bank friends. We got to check both bank friend and FERT. All right, fertilizer. So let's check this. Bank friend and microloan. 0.5. Okay, these are very highly correlated, which makes sense. If you know someone at the bank, they probably can help you get your loan application approved. You're probably much more likely to get a microloan. All right, so that's good. Now, is knowing someone at the bank going to affect how much fertilizer you use? Let's think about it. 0.04. That's very low. All right, bank friend is a really good exclusion restriction. So let's use that one. Bank friend. That's going to be our exclusion restriction. Okay, let's use bank friend as our exclusion restriction. All right, so there we go. Step 1 is to estimate the appropriate model of the selection decision, and it needs to include an exclusion restriction, which is going to be bank friend. So let's estimate that. All right, well, let's shrink that. Okay, and as we would expect, bank friend is significant in the selection equation, which is important. All right, so now we need to calculate the inverse Mills ratio. All right, we're just going to do it the easy way. And we're just going to use the predict command. We can do predict, and we're going to create inverse Mills ratio, all right, comma score. All right, so basically Stata allows you to calculate it automatically. All right, so inverse Mills ratio, comma score. Is that right? Yeah. All right, so now we have our inverse Mills ratio, and then what do? We go back. So this is step 2. Include the inverse Mills ratio in the OLS regression. All right, so now step 2, we go back to our original model, reg FERT on income, education, and the inverse Mills ratio. All right, and now remember, we're going to be looking for the coefficient on the inverse Mills ratio. If it's significant, that would suggest that we did have bias due to the selection process, due to the incidental truncation, which means we needed to use it. All right, now I'm just for comparison, I'm going to bring this down, the naive model down, just so we can compare them. All right, so here's our naive model again. All right, and then here's our model with the inverse Mills ratio. Oh, I put them in different order. Let me redo this with them in the same order just so it's easier to see. All right, edu, easier to compare. All right, let's do this again. All right, boom. All right, so let's compare them. Okay, so the inverse Mills ratio is actually insignificant. It's kind of close, but it's insignificant. If the inverse Mills ratio is insignificant, that means that we do not have evidence to suggest that the selection process, that means the incidental truncation, actually causes bias. In that case, we can use just the regular ordinary least squares regression. However, if the inverse Mills ratio was significant, then that would mean that we would need to report these estimates, the estimates from the Heckman model, because these would be unbiased. All right, so in this particular example, the inverse Mills ratio is insignificant. That means we don't have bias due to incidental truncation. All right, in this particular approach. All right, so that's doing it by hand. But now let's use the Stata software package. Now, the Stata software package does this using a little bit more of a more nuanced approach, so it's going to be a little bit more complicated. It'll yield a little bit different results than when we do it by hand. In practice, I use the Stata software package, but I did this by hand just to illustrate it, right? Just to kind of go through the process of illustrating it. All right, so let's do it. Heckman model. So what we do, Heckman model, is we write basically the OLS regression, all right, comma, selection, and then in the selection, we write out the selection model. So microloan equals edu, income, and then the exclusion restriction bank friend there. All right, so we can use this, and it's going to give us a result. All right, so here is our Heckman sample selection result. Here are coefficients from the selection model that controls for the selection. All right, here's our model from the first stage probit. All right, and then this eighth row, this /8th row, this is the estimated. It's a little bit nuanced what they're doing in the program, but basically this is what is going to represent our coefficient on the inverse Mills ratio. All right, and so in this example, so using the richer approach that the Stata software program uses with the Heckman model, we find that the eighth row is significant. So that means if this is significant here, that indicates to us that we did have bias as a result of the incidental truncation, in which case we need to use these coefficients. These will be our unbiased coefficients instead of the naive model. So basically, we can compare the Heckman model to the naive model, and we will compare them. We'll see that the naive model had biased estimates, a biased estimate of education, a biased estimate of income. Due to the incidental truncation, we can see that we have evidence of incidental truncation by seeing that the eighth row variable is statistically significant. Okay, so there we go. That is it. That is incidental truncation. When you solve incidental truncation in practice, go ahead and use the canned software program. It uses a more nuanced approach. I did it by hand to kind of illustrate it. All right, so thank you very much. I hope that you enjoyed the lecture, and I hope that you have a great day.